and you're looking at the volume. These were the three different elements. Last time we looked through an example which is based on a line element. Now we're going to look at an example for the area, and so far we looked through what we call as the method of integration. And this thing works for what we call as the continuous systems. And then we're going to also look at the what we call as the discrete systems, where you use the formulas where you use what we call as the summation sign, and these ones are all with the integration. So the example we get to work with is, let's say you have x is x and a y, then you have an area, and this area is given by y equals to k x squared and the coordinates of this point, or this one here is A, this one here is H, and here's the area. The question here is to find the coordinates of the centroid of the shaded area. We want to find the centroid at the shaded area given by this here, and what we're going to assume is that that's the cross section, and you have half the solid in the front and you have half the solid at the back, which means your z coordinate for the centroid will go to 0. Okay, so that leaves us with two more equations. You have the equation for x bar, that's going to be area integral dA, and you take the area integral x tilde dA, and then you have y bar, which is another area integral dA, and y tilde dA. So these are going to be the two equations, and in that equation you need to find this, which is really the area of the shaded part. Then we need the x tilde, we need the y tilde, then we want to find this integration, and then we need to find this integration. So if I redraw this diagram, then from the diagram you can see that this coordinate is going to be A and H. Then from the equation we have, I could write H equals Ka squared, or K becomes H over A squared, which means this equation could be given by y equals to H over A squared and x squared, and that's just done to bring all the variables to a common number. Then we pick a small element. I take a rectangle here, and let's take this rectangle as some distance x, and it has a thickness of dx. So that's the rectangle which we choose, And the idea here is that this whole area is made of small rectangles which are going like this. So you have, let's say, this rectangle here. So the entire area is added up as this rectangle, this, and this. So we just pick one of those. So that becomes our representative rectangle. And I'm going to take this height, this thing here, as y. So for this rectangle here, the area, which is dA, that's going to be y times d of x. It's just the height, and you multiply it by the width, in this case happened to be dx. So that's just this part. Then I could draw lines at the center. And we look for the centroid of this rectangle. So if that's the C, then its coordinate is going to be x tilde and y tilde. So it's the rectangle for which, if you locate the centroids, those are going to be the x tilde. For which, if you locate the centroids, those are going to be the x tilde and y tilde. So from that diagram, x tilde is going to be x, this length here, half of the width, that's dx over 2. Then your y coordinate for the centroid of this rectangle is at half of the height, so that becomes y over 2. Then we do one more thing. We know that in the limiting sense, dx can approach 0. So dx as such is really a small number, which means you could drop this to 0, and we can approximate x tilde by x, which means the area. We look at area, which is going to be area integral dA, and we know the dA is y dx. And this here is given by this equation. So you go h over a square, then you have x square, and you have dx. And then next thing we need is to see how it could be integrated. So you're going to go from x as 0, and then you go from x equals to a. That defines the endpoint for that diagram. So you're going to go from 0 up to a. And that should give us the shaded area. I mean, that's exactly what you have done in calculus when you were trying to find the areas for given curves. So we're looking at from 0 to a, h over a square, x squared dx, and that comes out to be h square x cubed over 3, and you're going to go from 0 to a. So that should be, we're looking at h a over 3. So that's what you get as the area. Then we need the next integration, that's x tilde and dA. Again, that's the area integral. So you're looking at this, x dA would be y dx, and your limit's going to go from 0, and you're going to go here to a. So that's x. Again, we're going to replace the y by h over a square x square dx. You're going from 0 to a. So in here, I can take the h over a square out, that's constant, and you have 0 to a x cubed dx. And that's going to go as h over a square, x fourth over fourth. We're going from 0 to a, so that's h. It's going to be a fourth. You divide by a square, it gives you h a square over fourth. So that's the second integration we need. Then the third one, that's y tilde and dA. So here y tilde is y over 2, dA is y dx, and your limit's going to go from 0 all the way up to a. So that's 1/2 0 to a. You have y and a y, that's the y square, and that could become h square a fourth, x fourth, and dx. So that would be 1/2 h square a fourth, and then this is going to go to x5 over 5 with the limit 0 to a. So we get h square. That's going to be a fifth. You divide by the fourth, so you get a, then you have a 10. So that's your third integration. So now we can find the x bar for the entire area. So you go here, you have h a over 3. That's from here, and then we have this, so you go h a square over 4, and that should give you 3/4 a. That's one coordinate. Then we go y bar, you divide by the area, which is h a over 3, then you divide by this, that's h square a over 10th, and in this case you get 3/10 of nh. So basically what you need is these are equations, and then you need to find whole series of integrals to